Okay, so we just talked about how to evaluate double integrals over rectangular regions, which is nice because it's very related to um, evaluating something like partial derivatives. So one of our components is constant, and you just basically go back to single variable calculus. What's a little bit more interesting is when we integrate over non-rectangular regions, because it's not quite as easy to set up the limits like we did in the first section. So I think that the best way to think about more interesting integrals like this over non-rectangular regions is to divide the scenarios into two basic categories. So the first category is kind of what we're used to seeing, where on the x-axis, we have these two sort of well-defined limits. I'm going to call them a and b. So we're integrating from a to b on the x-axis, and then the y-axis is going to be a little bit more interesting. So the y-axis has some sort of like curvy component like this. So the y-axis maybe has some functional limits. I'm going to call them g of x on the bottom and h of x on the top. So our region maybe looks something like this, but the important thing to observe is that the x limits are just regular old numbers. There's like nothing curvy going on here. That's scenario number one. Now the other I guess scenario is basically just the opposite of this. So instead of having our nice numerical limits on the x-axis, we could have them on the y-axis instead. So maybe on the y-axis, we're integrating from some constant value, I'm going to call it c, to some other constant value, I'm going to call it d. And then on the x-axis, that's the one where we have some curvy, not function because it doesn't pass the vertical line test, but some curvy relation here. So I don't know what this is going to look like, something like that. And then I'm going to call these expressions here, let's see, let's call this g of y, and then this is going to be h of y. So these are our two basic scenarios. Now, you don't really have to remember two different things, two different rules in order to integrate with these. The most important thing that you have to remember, and it's constant throughout the entire all the sections on double integrals, is that your numerical limits, this nice a and b, and then over here the c and the d, are always the last thing that you're going to do. So like on this first one, you're going to integrate from a to b second. And a to b in this first scenario corresponds to x limits. So I know that the a to b outside integral is going to be with respect to x. And then the second integral is kind of like exactly what you would expect it to be, except your limits are a little bit different. But now you're integrating from here, the bottom of this one, so that's g of x, that first function, up to h of x. And when we're integrating this way, vertically, we're integrating with respect to y. And then, of course, like normal, we're going to have some two variable function on the inside here. But the important thing to notice is that these numerical limits happen on your outside integral. So using that idea, we can go over to this one and see how we would maybe change the integral. So in this case, our numerical limits happen on the y-axis. So we know those need to go on the outside. We're going to integrate from c to d, but that corresponds to our integral in terms of y. So we're integrating with respect to y second. And then the first thing that we'll do on this one, the inside integral, is going to go from g of y to h of y. And this is going to be with respect to x. So either way, it's important that your nice numerical limits are on the outside, and then after that you just sort of integrate like normal and do what you've been doing with the double integrals in the first section. So let's see how this goes on our first picture. Now a lot of times on these exercises, it's going to describe the region and not provide you a picture, and it's not going to tell you an order here. It's just going to give you some double integral over this region. And we don't really know what this region looks like, so I'm not sure if it falls into scenario 1 over here on the left or scenario 2 on the right. So on all of these examples, and I think on the exercises, I've given just like a little graph picture, because I think that at least for me, that helps me a lot to decide kind of my order of integration. It helps me to decide where my numerical limits are. So I'm just going to start by graphing these functions. Let's see, y equals 1/2 x. Well, that's just a simple line with a slope of 1/2. So pretty basic so far, kind of like that. And then y equals the square root of x, passes through 0, 0, passes through 1, 1, and passes through 4, 2, like that. So it's going to go something like this, which kind of leaves this little enclosed region in here, which I'm guessing is where we're integrating. So then it says x equals 2, so that's starting here, and x equals 4, so that's here. Now notice when it just says x equals 2 to 4, those are our nice numerical limits. So I can tell on this one, I'm integrating with respect to x from 2 to 4. I'm integrating with respect to x second, because that's the sort of friendlier, more numerical integral. So that's what I do second, which means that my inside integral is going to go on the y-axis from the bottom function here, which is that 1/2 x. So 1/2 x up to the square root of x, and this is with respect to y. So here's my setup for the integral. That hasn't taken into account the integrand at all because that has to be given to you in the problem. In this particular problem, the height of the function, the height of these rectangular prisms that we're adding up on the z-axis is the function xy. So this is my actual integral, and now I'm going to go through and do this just like I did in the first section. So I'm basically going to consider only this inside integral first. And when we're integrating with respect to y, remember that x is a constant. So I just treat it just like I would like a 5 in the integral. So I'm actually going to do this separately here. I'm integrating from 1/2 x to the square root of x of xy dy. Now, x is a constant in this case, so my integral is going to be x and then y squared over 2. And I'm evaluating that from 1/2 x to the square root of x. So we're still going to end up with some variable expression in this problem, or in the inside integral, and then when we go through and do our numerical limits on the second integral, we're going to just get like a numerical answer. But that's why it's important to do the numerical limits second, because that's what gives us a nice answer in the end. So when I plug in the top limit, this turns into x times, and then square root of x squared is just x over 2 minus, and then x times, well, 1/2 x quantity squared is 1/4 x squared all over 2. So when I simplify this, this becomes x squared over 2 minus x cubed over 8. And again, not a numerical answer, but that's okay. I'm going to go through and integrate it again anyway. So now I'm on to my outside integral, which goes from 2 to 4. This is my new integrand, x squared over 2 minus x cubed over 8. And notice this is back to single variable calculus. Nothing is weird here. So when you evaluate that, you're going to get, what, x to the third over 6 minus x to the fourth over 32, and we're evaluating from 2 to 4. So if you want to pause the video, you can do that now. It gets a little bit ugly with fractions when you're actually evaluating this thing. But I'm going to just write down the answer in a second. So if you want to pause the video and go through and work out this computation, you can do so now. So when you work all of these things out, in the end, you get a volume of 11 over 6 cubic units, whatever those are. So 11 over 6 is the answer. Also, since that's positive, it tells you that at least most of the area, if not, or sorry, most of the volume, if not all of the volume, is above the xy plane, so in the positive z realm, because we got a positive volume answer. So we'll do one more of these kind of basic ones and then a slightly more interesting example on the next page. So this next one, again, it's just sort of like describing the region. It doesn't give you a picture. So I think the first step on this problem, again, is to draw what this graph, what this region looks like. So y equals negative x plus 1 has a slope of negative 1 and crosses through the y-axis at 1. I'm going to continue this up this way just a little bit, like that. And then y equals x plus 1, well, same thing except with a positive slope, but same y-intercept, so I'm going to, like that. These things cross at a perpendicular. And then the line y equals 3, so that's 1, 2, 3 steps up here. Now, I know it didn't give us two numerical values for y. We only have this y equals 3, which sort of suggests that maybe this is scenario 2. The other value is sort of built into the first two functions because they have an intersection point. So I think our first limit on the y-axis is y equals 1, but it just sort of inherently exists because those original two functions intersect anyway. So this is our region, this is our triangular region, and we're in scenario number 2 with our limits sort of on the y-axis, which means our outside integral from 1 to 3 corresponds to y. Now, here's something a little bit interesting. Since our outside limits correspond to y, that means everything else in here, the inside integral is going to all be in the language of x, which means on the bottom here I need to have x equals something, because really, like, on these two outside limits, this means y equals 1 and y equals 3, plus 1. Y equals 1 and y equals 3. So I really need like x equals something here and then x equals something here because I need this inside integral to completely be in the language of x. And I'm pointing that out because these two functions that are going to give us the limits, right, from here to here, are not in the language of x right now. They're in the language of y. Y equals all of this. Y equals all of this. So I need to take these functions and before I do anything else, change them around a little bit so that they're in the language of x. So the first one becomes x equals 1 minus y, and the second one becomes x equals y minus 1. So this first function is going to be my bottom limit here, 1 minus y on the bottom limit, and then the top one is going to be y minus 1. And all of this is in the language of x, and then my integrand given to me in the problem is 2x minus y squared. So now I'm set up for integration. I just have to do it in the correct order, which means integrate from the inside here first. I don't have a lot of room for this one. My first integral is going to go from 1 minus y to y minus 1 of 2x minus y squared, and this is all with respect to x, which means anything with y is a constant. So my first term here integrates to x squared, and my second term here, since that's a constant, is just going to be xy squared. And then we're evaluating from 1 minus y to y minus 1. So I'm going to plug those in, and this gets pretty ugly for a second, but when I simplify it, this entire thing, when I evaluate and simplify becomes, what do I have written down? Let's see, negative 2y cubed plus 2y squared. Negative 2y cubed plus 2y squared. So if you want to pause the video and get, there's a whole lot of details that happened here. So you're plugging in the top limit, plugging in the bottom limit, and also I should note when I say plugging in the top limit, you're plugging that in for the x value only. It only goes in for x. Y is just going to stay because y is not our variable of integration in this first portion. When you get to this point, then we will keep integrating. So now I'm going to do my second integral, which is going to go from 1 to 3, and now this one is with respect to y. So at this point, all of the x's have gone away, and I'm going to get a nice numerical answer when I'm done, and that's going to be the volume of this original two-variable function on this region. So we're kind of back to single variable calculus, right? So the integral of 2y, or of negative 2y cubed is negative 2y to the fourth over 4. And then the integral of 2y squared is plus 2y cubed over 3. And then I just need to evaluate from 1 to 3. Now I'm going to simplify this just real quick and say negative y to the fourth over 2. So when I plug in 3, I get negative, let's see, 81 over 2. And when I plug in 3 here, 2 times 27 is 54 over 3. So there's my first portion of this, and then I'm going to subtract what goes on when I plug in 1. So this is going to be minus 1/2 and then plus 2 thirds. So when I distribute that negative here, I'm going to get negative 81 halves plus 54 over 3 is 18. So I'm just going to simplify that. And then minus negative, so I really have plus 1/2 here, and then minus this 2 thirds. So for this next step, I'm just going to put the negative 81 halves and the 1/2 together, which gives me negative 80 over 2, or in other words, negative 40. So I have negative 40 plus 18, which gives me, oh gosh, what, negative 22? And then minus 2 thirds. So to get my common denominator here, I have negative 66 thirds minus 2 thirds, which gives me a final answer of negative 68 thirds. Sorry, that's so messy at the end there. So negative 68 thirds, and this is a unit of volume, which also tells us that at least a portion of the volume, well, if we were looking at this in 3 dimensions, and we could actually see what this looks like on the z-axis, at least a portion of this would lie below this plane, because it's giving us a negative volume answer, so it must be sort of negative in the z world. The last example on here is a little bit more interesting because it really doesn't describe the region in the same way that the first 2 examples do. So this one says, find the volume of the solid bounded by the cylinder x squared plus y squared equals 4. Now, this looks like a two-dimensional equation. In fact, we know exactly what that looks like. It's a circle of radius 2. It's a terrible circle, but I'm going to stick with it. A circle of radius 2 centered at the origin. Now, one thing about this is that's not a nice function, but one of the things we could do with that is say y squared equals 4 minus x squared, and then we could actually describe it as y equals plus or minus the square root of 4 minus x squared, which is going to help us in just a second. And then it says, and the planes y plus z equals 4 and z equals 0. Well, this is interesting because we're not, we haven't yet, and we won't integrate with any limits in terms of z in this section in double integrals. So the place that the z comes in is in the integrand. So what this is telling us in the second portion of this is what is the integrand. This is going to go into the integral. So another way that I can write this is z equals 4 minus y. And it's saying and z equals 0 just because that's always how integrals work. We start at the sort of 0 level and then compute our area or our volume up to some other function. So here's our function. So as soon as I'm done setting all of this up, my integrand is going to be 4 minus y. So now I just have to decide which scenario I'm in and how to compute the limits of this and then integrate in the correct order. So I've got y described in terms of x, which sort of suggests maybe these should be some limits that we use. So like maybe I should think about y going from this curvy function here to this curvy function here. So 2 different ones. I'll use a different color to show this a little bit better. This would be the top function, and then the blue one down here would be the bottom function. So the curvy stuff is happening with y, which means it needs to happen first. So this would go from negative square root of 4 minus x squared to positive square root of 4 minus x squared. And then the x values, notice they're not given to you in the problem at all because they're sort of already defined by the original equations. X is going to go from negative 2 to positive 2, and that's what we'll do last. So the dx happens last and dy happens first, and then we'll just go back to this in normal order. So starting with your y integral at the beginning. I'm going to give myself some more space. So when I start with my original integral, I'm positive square root of 4 minus x squared of 4 minus y with respect to y. 4 integrates to 4y, and y integrates to negative, let's see, y squared over 2, and I'm evaluating. This looks like it's going to be terrible, but actually I'm going to plug the square root into a square, so it's going to actually simplify this a little bit here in a second. 4 minus x squared. So plugging in my top limit first, everywhere I see a y, I get 4 times the square root of 4 minus x squared minus, and then I'm putting this in for y, so I'm squaring it, which becomes 4 minus x squared with no square root because I squared it away, over 2. So there's my first component with the top limit plugged in, and then I'm going to subtract and do this again. 4 times, well, negative square root of 4 minus x squared minus, now when I square this bottom limit, the negative sign goes away anyway, and so does the square root, just like it did a second ago, over 2. So when I expand this all out and distribute my negatives, I have 4 square root of 4 minus x squared minus the quantity 4 minus x squared all over 2, plus, because I'm going to have minus and negative here, so plus 4 times the quantity square root of 4 minus x squared, and then minus negative again, plus that quantity all over 2. Now this is nice because these two cancel out. I had the negative component here and the positive component, those two cancel out, which leaves me with 2 identical terms here added together, so 8 times the square root of 4 minus x squared. And that becomes my new integrand. Now the new integrand is all in terms of x. We're integrating from negative 2 to positive 2. 8 times the square root of 4 minus x squared dx. Regular old single variable calculus integral. Now one thing that's kind of interesting, we can pull the 8 out to the front, and this looks like a fairly simple integrand, but if you try to do u substitution, it actually doesn't work here. So think about, this is probably in your, well, if you had Calc AB with me, definitely one of the first integrals that we ever talked about was this integral. Before you knew any methods of integration, you learned how to integrate this integrand by just thinking about what it looks like on a graph. And what that thing looks like on a graph is the upper half of a circle of radius 2, so positive 2 and negative 2, just the upper half of a circle. So the area of that is going to be pi r squared, but then over 2 because it's only a half circle. So pi times r squared is 4 over 2. In other words, the area of this is 2 pi. So since integral means area under the curve, this really becomes 8 times that area, 2 pi, or 16 pi, and that is our final answer. So 16 pi units of volume on this one. The only thing that's really difficult about some of these is sort of getting through the first couple of steps, because once you set up your integral, it really becomes, just like doing the steps in order. I think the challenge is looking at the picture and deciding which variable should go first, which variable should go second, and actually there are different ways to do this problem. I just chose to set it up in terms of y first and integrate that way, but you could have done this in opposite order and you would have gotten the same answer. So at this point, you can either continue on to the third part of the lesson and talk about triple integrals, which are actually really not very challenging at all, or you're ready for problems. Let's see, this one is still rectangular. I think problem number 5 is the first one that starts with these weird non-numerical limits in the integral. So you can do problem number 5 now, even though you didn't have to set this up. It's still a double integral with some strange limits. Number 6, same idea, just practicing. 7 again. And number 8, you'll have to set up your own integral. Whoops. You'll have to set up your own integral because I described the region here, so you're going to have to decide on the order. But you're ready now to do exercises all the way up through 8, or you can continue on to part 3 of the video and think about triple integrals before you do that.